All right, we have a guest speaker. We have Sheldon Wasik. Uh, did I pronounce your name correctly?
Yeah, you did. Good job.
Excellent, excellent, excellent. Uh, and you're going to, let's see, you're going to talk about spectrum and, well, basically the spectrum.
Sure. Yeah. Yeah.
All right, let's see. Do you want to introduce yourself and tell us about your background and all that kind of good stuff?
Sure. Yeah. So I'm Sheldon. Well, my title is Zone Regulatory Services Coordinator. Sounds super fancy. But I work for the National Radio Astronomy Observatory. And my role there is mostly as the National Radio Quiet Zone Program Administrator. So what I do is I can actually, you know what? Let me just share my slides
You're welcome.
to go for that. Um,
You'll be able to.
let's see. It says it's
Oh,
disabled.
multiple. Now I got it.
Okay, there it is. Um, let's see what this does.
Ooh.
Um, Okay, yes, this is probably a better way to introduce myself. So, yep, so I'm Sheldon. Like I said, I'm the Zone Regulatory Services Coordinator. My main role with that is I'm the National Radio Quiet Zone Program Administrator, basically, with a little bit of roles now involved in the Puerto Rico Coordination Zone, which I'll get into here. But my job there is to help the quiet zone facilities. Mostly my role is for the Green Bank telescope, which you can see up here on the slide. So I help protect it from transmitters and interference for that, for the site basically. So when a transmitter wants to come into the National Radio Quiet Zone, they have to coordinate through me. And what I'll do is I'll run a propagation study and some calculations to figure out if there's going to be interference at the telescope or not. And I'll talk a little bit more about the National Radio Quiet Zone during this presentation, but we get the luxury, we are one of the only places in the whole world that get the luxury of protecting our scientific equipment with some sort of federal regulation on spectrum. Because, spectrum, I'm sure you're learning quickly, is this resource that everybody is after, but everybody also wants to protect at the same time. So yeah, I have this very unique role at the National Radio Astronomy Observatory on behalf of the Quiet Zone. So I also, my more of my background is I studied astrophysics at Michigan State, just a bachelor's. I'm sure you've had a wide range of talks from bachelor candidates to postdocs to everything in between. I have a bachelor's and I did a lot of research at Michigan State in theoretical astrophysics, which then, led me into this role of the spectrum work that I do at NRAO now. They strangely gave me the same skills to work on real world spectrum comparing theoretical, but that's, a different topic. Feel free to reach out to me if you have any questions of, how I jumped from theory to the real world spectrum. I'm happy to answer anyone's questions along the way. Yep, and like I said, I eventually ended up in my role at the National Radio Astronomy Observatory here. So my role is the Zone Regulatory Services Coordinator. Sounds super fancy once again, because NRAO has recently adopted the Puerto Rico Coordination Zone for the next couple of years, and it kind of runs side by side with the National Radio Quiet Zone. So I'm helping out with some of those efforts. And I know this, ham radio is a big topic of this class, and within the National Radio Quiet Zone, we deal with ham operators quite often, especially in the summer months. So I'll talk about that during some of this presentation. Right. So these are some of the topics that I'll talk about during this talk. What exactly is the National Radio Quiet Zone? You hear the word quiet. Is there really no radio frequency devices? Not quite. That's going to be one of the really interesting topics where engineers get to explore a little bit. Some engineers might struggle. Some engineers probably enjoy it a little bit more than others. But I can explain some of that as we get farther on in this presentation. Um, how is the NRQZ, National Radio Quiet Zone, different than most of the world around it? I'm sure you can start to imagine there's a lot of engineering challenges. Spectrum use might be limited in the quiet zone compared to elsewhere, or it might be the complete opposite for certain cases. I can kind of jump around that a little bit as well. Challenges engineers face, kind of the same two topics. Then I'll also talk about some ham radio in the NRQZ, because it serves a very unique role. It's very different than some of the other spectrum coordination efforts in the whole National Radio Quiet Zone, just because of the licensing that hams go through compared to the licensing that, say, a cell tower will go through. I'll also talk a little bit about ham radio at other radio astronomy sites, mostly the Arecibo Observatory that is in Puerto Rico, mostly because I kind of learned that aspect of it a little bit more. And we have some very good colleagues who have done some great ham projects on behalf of Arecibo. So I'm happy to talk about that with all of you guys. And just the role and future of spectrum management. Spectrum management, it's a very dynamic environment right now, and there's a lot of different roles that you can get into, whether it's licensing, whether it's engineering, and everything in between. So I'll just kind of talk through some of those and some of the other small little projects that I've done at NRAO while I've been here. So what exactly is the National Radio Quiet Zone, right? It's the scary thing that if you give it a quick Google search, you'll see articles of Wi-Fi isn't allowed in the whole zone, or there's no cell service anywhere. I'm not sure where most of you are located, but to give you some sort of size perspective, the National Radio Quiet Zone is shown over on the right. It's 13,000 square miles, and it encompasses, about half of Virginia, half of West Virginia, just the tail of Maryland. So it's a lot bigger than most people think. And for reference, my office is in Charlottesville, Virginia, which, actually slices the National Radio Quiet Zone in half, or the National Radio Quiet Zone slices Charlottesville in half, where I'm protecting the Green Bank Observatory, which is kind of in the middle of nowhere, West Virginia. It'll take me about 2.5 hours to drive there. And, I'm not even across the whole zone. I get cell service in some parts of it. I get cell service I don't get cell service in some parts of it. So it's very much an engineering problem, but we also, like I said, get to protect our sites in the quiet zone, the Green Bank Observatory, which is, for radio astronomy. And then if you ever take a look at the NRQZ a little bit deeper, you'll also notice that there's the Sugar Grove research station, which is basically a DoD site. It was initially set up by the Navy back in the 50s, and that's kind of how the history of the quiet zones shifted. So I am the front for both Green Bank and Sugar Grove, but I basically only communicate over to Sugar Grove while I run the analysis for Green Bank. So to give a little bit more information on the quiet zone, what's the legal aspect of it when you think about the spectrum of it? Coordination is required for permanent fixed transmitters, both specified by the FCC, as well as the National Telecommunications and Information Administrative, NTIA. Basically, the FCC is the commercial side of spectrum, and the NTIA is the federal side of spectrum. So there's legal writing in both of those systems and both of those laws for any permanent fixed transmitter to basically coordinate through us to make sure there's no interference to all of our sites. So, what are we trying to protect, right? I said mostly, my talk is going to be geared a lot more towards Green Bank and radio astronomy, just because that's the side that I deal with. So the Green Bank telescope is, what we're trying to protect, what I'm trying to protect when I talk about interference. It is the world's largest fully steerable radio telescope. So it does a full 360-degree rotation. Fun fact, it can actually spin around that full 360 degrees in about 10 to 15 minutes, depending on how much you want to push it, which is quite fascinating with how big it is. It's a 100-meter diameter dish, and it's taller than the Statue of Liberty for some size perspectives. if you Google around and find some pictures of it, it might not look that big on a picture, but trust me, it's it's quite a large object. The Green Wing telescope, it has an operating range of basically 0.1 to 116 gigahertz, so it can do almost any type of radio science that you want it to do. The science of it is changing a little bit because it was built about 20 years ago, and just radio astronomy has kind of shifted in the frequencies that they look at. But the luxury that we have is we get to, protect for the whole frequency range if we want to. It gets about 6,500 hours of observing every year. So that's one of the highest percentages of radio telescopes in the world that are observing versus in maintenance. It is also, so just some fun facts about the GBT is the surface is smooth enough to a noise level of 260 microns, or about 5 human hairs. You could see a quarter about 3 miles away, which is pretty cool. And it weighs, like I said, almost 17 million pounds, which is quite significant when you have to think about, I think there's 16 wheels on it. So how much, there's what, about 2 million, 4 million pounds per wheel, which is quite significant when you think about it as an engineering perspective. So science from the GBT. So what kind of stuff are we doing? What are we actually protecting that comes out of it? I'll just start by saying the GBT does just about every type of radio astronomy science that you can think of. Some of the main ones that have kind of popped up in the news lately, it maps gravitational waves from pulsars, and a pulsar is a highly magnetized rotating neutron star. They are essentially used, as the universe's clocks, along with some other objects in the universe, as well as being able to map gravitational waves from a pulsar from Earth is one of the new things that's been done in astronomy. It's projects that have taken 15, 20 years to develop. So being able to protect something like that is really cool to see. The GPT also does galaxy mapping, so we know where star formation regions are happening. We know where expected black holes are, where supernovae are likely to blow up in the future, things like that. So it's really cool to see, coming from an astronomy background, especially, that I get to see the science that comes out of it while working my everyday job, basically. So I don't know if you guys have seen one of these charts yet. This is basically all of the different frequency allocations that are, I guess, public in a way. So what this is, think of your cell phone frequencies, think of your TV stations, think of your radio stations, your protected passive bands that are used for Earth monitoring. So this all encompasses, that's all encompassed in this chart. And this chart's really important to us, mainly because basically it's every type of application that we could receive, right? It's everything that could potentially cause interference to the radio astronomy site, but it's also the the true license holder of that spectrum. So when we talk about spectrum, it's this finite resource that people try to grab as much of, or what they need to, in order to communicate in whatever way. So this is just a good visualization to us of how busy it can actually be out there, and an idea of the protections and things like that. So what exactly happens in the National Radio Quiet Zone and the coordination behind it? So radio sources are allowed in the quiet zone, to no surprise. The way that we do it is we use these really funky units that is called the power flux density limit, and it's how much power is coming through a unit area per time, basically. It's set by the International Telecommunication Union, which is basically the international level of spectrum allocations, because you can imagine, different countries like to use different spectrum in different ways for innovations, for different technologies. So the ITU kind of is a good international representation of this, and making sure everyone is behaving, basically. So we're a frequency dependent power flux density limit for radio astronomy, which means the different frequencies that you use are going to affect the telescope in different ways. And we also are protected by what's called the West Virginia Radio Astronomy Zoning Act, which if you read into the fine details of what's actually protected under the NRQZ laws, you'll notice it's really only fixed transmitters. So the West Virginia Radio Astronomy Zoning Act is a basically a nice way for us to be protected super close to the observatory by any sort of electronical device. It gets more restrictive the closer you get to Green Bank. It's also often more restrictive than the NRQZ limits. So these are things like Wi-Fi routers, ham radios, cell phones, things like that, that wouldn't fall under the NRQZ law, but we get some protection from. So the way that I'll, take a look at some of these calculations is in a way, I'm just looking at what is the received field going to be from a certain transmitter, and is that going to impact our science that comes out of the telescope? And that's kind of represented by a very, very simple equation right there. It's just, your transmitter power, your gain, and then you subtract the losses. I mean, in practice, it works. It works pretty well in principle. In practice, we have to allow for some re-engineering of designs. So let's say a TV station wants to put up a tower 20 miles away from the telescope, but it's going to be well above our limits and going to impact the telescope significantly. We'll provide them with some assistance and basically give them a power level that we want them to meet based off of our models, and then they can kind of work with us to make sure that that's met. That's also a little bit to help the licensing agencies, which were once again the FCC and NTIA, to kind of see where we're coming from, to kind of understand what the limit should be and things like that. Because like I said, the really funky power flux density limit, that unit is not used throughout a lot of radio spectrum users. You often see, watts and ERP rather than the radio astronomy limits. So we do allow for, antenna directionality, transmitter power, antenna down tilt, and additional shielding to be met when applicants are in a re-engineering process. That's kind of demonstrated by the plot on the right. This is just a handful of applicants. I think these are mostly cell towers and public safety systems. That kind of represents antenna directionality a little bit. So you'll notice the closer that you get to the two red dots, which are the two protected sites, most of the power is kind of pushed away with different antenna directions, as opposed to your typical omnidirectional or more three-sector designs, if that makes sense. So how do I exactly do this analysis? I'm sure you guys will learn or have learned that propagation models are used quite often in the radio frequency world. And what a propagation model is, if you're not quite aware, is it's a way to measure or quantify the amount of loss that's going to be between 2 points at a certain frequency, a certain power, things of that sort. So what we like to call it is total path attenuation. How much is your path going to attenuate, or another way to see it is how much path loss is a certain signal going to have from one point to the other. And we use these models to, basically be the core of our calculations to figure out what the power density is going to be at our really powerful telescopes, which are, very, very good at being a receiver. They're very large. And we also, for those who are more interested in propagation models, we use a combination of what we call free space losses, and then we either add a minimum of a troposcatter loss or a minimum of a diffraction loss. And I think this picture below the troposcatter diffraction does a great job at illustrating, what that is. Diffraction is, when you kind of crest over a peak and your radio signal almost bends over that peak and you get a loss due to that angle. Or tropospheric or tropospheric scatter is bouncing off the troposphere. So radio frequency signals kind of propagate many different ways. They have a lot of different losses associated to them. And it's kind of quite fascinating to see what some of these models are able to do, because it's cool that people are able to quantify it in a way. The plot up to the right is just a idea of kind of what's happening in these models as well. So what you're looking at is you're looking at the topography cut over a certain distance. So what that means is you're basically looking at mountains, and on the left is a transmitter, and on the right is our telescope. Um, so you're kind of getting an idea of what the terrain looks like in between the two sites. There's a lot of challenges that come with the quiet zone. One of those being, how do you coexist with something like emergency services, right? The plot to the right here is a coverage map of basically where Green Bank Observatory, NRAO, myself, would object in the red to a West Virginia statewide emergency system, or in the green, approve of it. And it's quite significant of where you're actually objecting to certain sites, because oftentimes those are on higher peaks where people actually want to put the sites. So it's kind of one of those battles in the spectrum world of how do you make things coexist, but also making sure that you're protected at the same time. So we're still struggling with that. There's been a lot of workarounds that we've done. There's a lot of different models that we've had to run. We've gotten assistance on federal levels to assist with this problem, but it's probably always going to be there. It's a challenge because we're basically federally obligated to comment on these facilities to protect our sites. Well, at the same time, human safety is probably of equal or higher importance to some of that. So it's one of those things that our directors do a very good job of addressing, and we're lucky for that. But it's going to be a challenge that's going to persist. An example, right? So this West Virginia statewide system lives somewhere between 450 and 470 megahertz. This is quite important to radio astronomy, because there's a new instrument at Green Bank, which is called the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Basically, it's mapping what we call fast radio bursts and pulsars in between 400 and 800 megahertz. And this is a very new type of astronomy, and kind of cutting edge research, where you have all of these mysterious signals kind of popping up, and they're extremely high energy, and they seem very random. But we think that there's some sort of correlation to either star formation or potentially even some sort of dark energy measurement. So it's important that we're still able to do this science. So that's an example of that. Other challenges in the quiet zone, Wi-Fi, right? Wi-Fi is big on interference for radio astronomy and other, even near band spectrum users. For that reason, Green Bank and the surrounding area is wired with fiber as much as possible, because fiber is an optical transmission, so it doesn't even cause any interference like a coax cable would, that you would usually, run on a wired connection. Or obviously there's cellular towers, which are other challenges that we face, because people like to tie cellular towers to economical development, even on public safety sometimes. But those are all still coordinated in the quiet zone, and those are, they cover a lot more range of frequencies than something like a public safety would. So giving up on the cellular problem would be losing a lot of important frequency spectrum to radio astronomy. Now I get to talk about ham radio in the NRQZ. So I myself am not a ham operator. I should have mentioned that earlier. Maybe someday. I think it can live very well side by side with radio astronomy, and a lot of my colleagues are ham operators, which is very cool to see. But a brief background on ham and the NRQZ is kind of like I talked about a little bit earlier. Coordination is really only required within 10 miles of Green Bank, based off of the West Virginia Radio Astronomy Zoning Act. And the reason for this, once again, is because the NRQZ laws is permanent fixed transmitters, and just about every ham is basically not going to fall under that. But what we communicate with hams all the time, because it's very great to see that community grow, and it gives a lot of education to understanding what we do. So we try to be cautious of that when we have to, think about limitations for them, or just growing that community in general. So we appreciate any voluntary coordination in the entire radio quiet zone, just because the less interference we have, the better and more science we can do. And also one of the reasons that we kind of reach out to some of these people for voluntary coordination is when you do get interference and you see it at a given time, if it is strong enough of a signal that is very concerning, it can take a lot of time to track down. So say if you see a 800 megahertz or 800 megahertz signal, you could almost attribute that to a cell band, but where is that cellular tower coming from? It can get extremely tricky, extremely fast. So if we are aware of what the RF environment is around the telescope at the time that we see the interference, we may have a little bit more luck in trying to track it down and just writing it off rather than spending 2 or 3 months of everyone's time. So kind of speaking more on the concerns that we do have of ham radios and the NRQZ is we're really concerned with line of sight of the telescope, as well as harmonics that the radios can give off. Mostly because Green Bank kind of starts to really do some of its core science about 400, 500, 600 megahertz nowadays. It used to do a lot of science back in like 100 megahertz areas, but just the environment of radio astronomy is kind of changing, and it's not really expected to be that low ever again. So the lower the frequency, often we tell hams, the better it is for Green Bank. And also we kind of make a note that other radio astronomy sites may differ, because there's, since Green Bank doesn't cover the 100 or 300 megahertz nowadays, maybe there's a new radio astronomy site over in Australia that all of a sudden is much more geared towards that, so that science is able to get done. And this is just a very busy US amateur radio band, and the power limits that you can have at those bands and whatnot, just illustrating how our power flux density limits kind of coexist with these amateur radio bands, where if you look at the NRQZ power flux density limits at the bottom right, you'll notice they're a lot lower, or a lot less restrictive, I should say, for frequencies below 54 megahertz, but then they start to get a little bit more restrictive as you kind of creep up in that frequency. So that's one of the main reasons we want hams to also be a little bit lower, is because it's a little bit easier to wash out that RFI if we do get some sort of interference. I'll obviously note that propagation characteristics play probably the most important role in this. If you're protected by a mountain, you're probably going to be a lot better off for us than if you're at the top of that mountain looking right down on us. But the general rule of thumb for around us is the lower in frequency, the better. So here's kind of some of the projects that I've interacted with the ham radio community quite a bit. There's a lot of weekend operators, especially in the summer. Campgrounds are in the area. There's a couple campgrounds within 6 miles. There's a couple of campgrounds within 15 to 20 miles as you start to get over a couple of ridges. And that's very cool to see that they reach out. They come from a wide variety of the country, of even the world. A lot will, like I said, spend a weekend there, spend even a week there, or things of that sort. So kind of some special events that we've kind of worked with the community with is there's several events that are annual events around the area. One of them is there's a motorbike race about 15 or 20 miles from Green Bank every year. And what hams like to do for that is they'll basically set up a transmitter and they'll bounce it off of a couple repeaters until they're able to get that signal over to surrounding communities and surrounding towns, so that they can hear what's going on at the race. It's a very cool project that they get to work on. Some of those are using a half-wave dipole, no higher than 30 feet at 100 watts, using a couple different bands. Those are often fine for us. And then a couple, there's other events that want to operate a little bit higher in frequency. So the second bullet point there is 3 to 4 times a year. What was pitched to us is a couple hams wanted to operate a little bit higher in the frequencies. So something like 144, 220, and 440 megahertz, upwards of 70 watts. And this was not great for us, but we wanted to find this opportunity to work with the community a little bit more. So we found some parts of the frequency that they were comfortable operating and were able to operate in, and worked with the green bank interference a little bit more. And then another example of some events that happen in the NRQZ, aside from just your typical campground weekend, is there was a ARRL sponsored 10 gigahertz and up radio contest. So I'm not sure the exact specifics of what these people were trying to accomplish, but I believe they're trying to send a millimeter wave as far as they could. Don't quote me on that. But they were using, fairly high gain, highly directional antennas up on one of the highest peaks in the quiet zone. And they wanted to do a full 360 degrees in azimuth. And since, a lot of basically the two sites in the quiet zone, Green Bank as well as Sugar Grove, are very sensitive to some of the projects that go on at those frequencies, much more than the low bands. We worked with this applicant to, make sure they were able to participate in this event while also meeting our limits or our requests. So what we decided with that is when they're within 20 degrees of our site, they would just turn off their transmitter and they just keep rotating until they got a couple degrees past, and then they'd start transmitting again and competing in the contest. So I think that worked out significantly well for them, and that was really cool to see. So yeah, once again, the general rule of thumb is most low band stuff will not interfere with our science. Within 10 miles, technically coordination is required, and we appreciate voluntary coordination. With the low bands, we're mostly concerned with harmonics, line of sight operations, just because anything that you start to get line of sight becomes a little iffy with how it starts to interfere. But we are, very happy to work with the ham community. We love seeing these events, the understanding for the engineering that goes on, the understanding for the licensing that goes on, and just it's cool to see. It's cool to see the community grow. One of the really great projects that have been good to work with is Summits on the Air, or SOTA. They're an amateur radio operating award program launched in Great Britain, actually. 24,000 participants worldwide, and about 7,000 of them are in the United States. And they've reached out to us many different times, just making sure we feel comfortable with them growing the project in the quiet zone, and making sure that their users as well understand the rules and legalities that come within the quiet zone, and some of the voluntary coordinations, what we're concerned about, like the line of sights and the harmonics. So what SOTA actually did is they developed an API for us to use, which basically works as they have a whole database of where their projects are active, and we can just communicate with that database without having to go through them. So it's one of those ways to, like I said, tracking down interference can be half the battle. With that API, that makes us feel a lot more comfortable with SOTA in the area, and I think they understood that. And we want SOTA to keep working, or not working, but operating and sending their information about the quiet zone out, and being able to enjoy the land, because it's a very beautiful area around Green Bank. A lot of valleys, a lot of rivers, a lot of mountains, a lot of cool ham projects that you're able to do. They also provide a lot of really cool detailed maps about every single radio zone in the world, everywhere from Australia to South Africa to the United States. This is just a quick snippet of their website on the right, and it kind of shows all of the really good peaks. It shows that 10-mile radius around Green Bank and the Sugar Grove station. And then below that, if you actually go and dig through the website, it can provide a little bit more details of how the SOTA users um, are able to travel and communicate in the areas, hotspots, and things like that. So it's a really cool project. We're very happy to work with SOTA. And we also have very similar communications with Parks on the Air. But I myself have just interacted with SOTA a little bit more. Yeah, so other radio astronomy sites, Arecibo Observatory, which is no longer operating. It collapsed a couple of years ago, which is really sad to hear. But the coordination efforts of the Puerto Rico Coordination Zone are still happening now, actually under National Radio Astronomy Observatory. So Angel Vasquez, who is the spectrum manager of the Puerto Rico Coordination Zone, which was home of Arecibo, he's great with the ham community. He's an operator himself. His call sign is up in this slide if you want to take a look later. But he has, he's taken a lot of pride in learning about radio astronomy throughout the years, engineering and science, as well as interacting with the community, because the environments around radio astronomy sites are very interesting. They're very cool to see what people around there learn about compared to people outside of there. So what Angel actually organized with Arecibo is they did a moon bounce with picking up the receive signal on the main Arecibo dish, and it actually made the front page of QST magazine, which is really cool to see. So there's Arecibo on the right on the front page of QST, and it brought. I think I remember talking to Angel. It brought over like 500 participants to the site, which was fascinating, because being able to teach a lot of the community about, well, one, bring the community together in a good way, and two, teach the community about why this radio astronomy instrument actually matters through hams is really cool. So that's also some of the things we're trying to mimic over at Green Bank, for example. But yeah, Angel is a great person to talk to about hams and the club that he ran out of Arecibo. He was also the first person out of Puerto Rico to contact people outside after Hurricane Maria hit the island in 2017 and all of the communications were down. And he did this with his ham radio, which was really cool. He ended up communicating hundreds of families' interests to their families on the mainland of the United States, and just kind of, you use ham that way. So all of this kind of falls under spectrum management. Spectrum management is this very broad term of, all of the engineering, allocation, licensing, hobbies even that fall under the radio frequency spectrum. And as, personal interests, whether it be public, private, hobbies, even interference of any sort, as that starts to increase, spectrum's becoming a lot more demanding, and we almost have to treat it like this natural resource in a way, because there's only so much of it, and it does contribute to all of the economic growth. It contributes to interests. It contributes to almost everything around us nowadays. And a lot of different fields are starting to come out of it, more prominently at least. So obviously you have your engineering, your licensings, but now we're starting to think about, how can these passive receivers like radio astronomy sites start to share a little bit more of the spectrum with things like cellular, for example, or things like satellite networks. And that's this idea of this dynamic spectrum sharing. And that's brought a lot of the software engineers to the spectrum world, which is also really cool to see, because mostly it's been a lot of policy people. It's been a lot of very niche engineering or very niche protection people. So the introduction of software is starting to be really cool to see in the spectrum world. Yeah, so it's just this big representation of a lot of sub interests. So there's been a lot of conferences that I've attended that are a lot of policy, software, engineering, and just meshing a lot of communities together, and being able to talk with all those communities has been fascinating, to say the least. So yeah, kind of bringing everything together. The NRQZ, it's a very unique area. It's one of the only areas in the world that has federal protections for federal facilities. And to no surprise, RF devices are not banned because the area is too large for that to happen. You would lose a lot of area of no coverage, whether it be cell phone service, even Wi-Fi, or anything like that. It's just not possible. So it's a lot more of a coordination area where people can coexist a little bit more. Engineers do face challenges in the quiet zone, but it's a fascinating problem to see solved time and time again. There's some very clever engineers that will use certain objects to shield so we don't receive interference from them, or they'll start to think of designs a new way, or think of how new technology can advance in the quiet zone to help better their systems versus our systems. Ham radio is also very important in the NRQZ. It's a good way to make the community aware of what radio frequency is, how one system can impact another, while also thinking about the trinkets that make up a system, whether it be a $100 made at home radio transmitter, or it's a multi-million-dollar radio telescope. They kind of all have the same core components in a way. Arecibo Observatory has demonstrated great projects with this in the ham world, and that's one of the areas I definitely want to push here, because it's fascinating work. It's a great act of both understanding science, but also wanting to make right with the people around you. And all of this, once again, all wrapped up in what we call spectrum management. It's a growing field, and it's a constant discussion at almost every level, whether it be economy, politics, hobbies. You think about it, it's probably there somewhere. Electric cars nowadays have to have this very strange discussion with spectrum, because they don't really want AM radio in their vehicles anymore because it causes interference. But then the AM community kind of backlashes, and you have this head on between politics, what used to be an economical game. So it's very cool to be working in the spectrum world right now. And I'm happy that I have the job that I do. I get to see some really cool astronomy that piques my interest, while also thinking about all of these bigger spectrum problems, if that makes sense. So yeah, that wraps up my presentation. So thank you, everyone, and I'm happy to answer any questions.
That was great. Go ahead. Someone's asking, I think.
Yeah, it's me, Messiah. So I don't know if I missed this part, but so since the NRTZ is it's an RF free zone?
So right, so it is it's more of an RF coordination zone. So the way that it's handled that in that direction. So if let's say you are a cell tower, right, and you're Verizon, you're trying to put up a new tower in the NRQZ, and you go to the FCC to get that license. In order for the FCC to license you, you have to coordinate with me, basically, and I have to say you're not going to interfere with the protected facilities in the NRQZ, and then the FCC will grant your license. So it's this extra precautionary step to protect the facilities in the area in order for them to get licensed. So it's not necessarily no RF or truly quiet as the name is. It's more of a coordination zone, if that makes sense.
Okay. And do other countries also have their own?
Yeah, there's a few that have them. Each one of them kind of operates slightly differently. One of the ones that comes to mind first is South Africa has a radio astronomy site that has their own protections. I don't know exactly what they call it. The astronomy site is called SKA. Another example is in Chile. They have some sort of coordination zone protections that are much smaller, because that is a site that's much more in the middle of nowhere, way up in the mountains. But there are a few around the world as you start to look around. Most of them do not have as much protections as the National Radio Quiet Zone, or most of them do not encompass as large of frequency spaces as the National Radio Quiet Zone. So it's very unique in that way, if that makes sense.
Good questions. Any more?
I
Well,
have a quick question. So I'm going to school in Socorro, New Mexico, and the VLA is like really close to here. Does it have similar protections as Green Bay, or like how does it differ?
Right. Yeah.
question.
So the VLA does not have similar protections. I believe the VLA has very short radius electronic protections, much more like the West Virginia radio astronomy zone. So that'd be more things like you can't have Wi-Fi a mile from the VLA. That's not going to be the limitations on like a cell phone, for example.
Hmm.
The VLA struggles a lot more with airborne transmitters, so things like airplanes, weather balloons, especially. So there's a very large NOAA weather center there that will launch like 1 or 2 balloons almost every week, and those can cause some pretty significant interference to the VLA. But yeah, no, to answer your question, VLA does not have this national radio quiet zone surrounding it, if that answers it.
All right, thank you.
Yep.
That's a good question. I, I'm curious about how does Starlink impact the National Quiet Zone?
Yeah, so to answer your question right away, it's not great, but what we've actually been doing with Starlink, and Starlink has been very, very great to work with. We've been running coordination experiments on behalf of the National Science Foundation. And the way that we've kind of ran these experiments is we've basically just taken random samples or coordinated samples with the Green Bank telescope and let SpaceX Starlink kind of just run their systems how they want to at that time, and trying to see if we can figure out where the strongest signals are, what the likelihood of damaging some of the science that comes out of it. And we're getting to a point where we think we can coexist a little bit more than say like your DirecTV satellite that's just fanning everything, because the nature of Starlink, which is very, very cool and very innovative technology, is they use a phased array beam that is about 11 kilometers wide on the ground.
Wow.
Yeah, so it's really cool. So they're able to do a lot more directionality than these large geostationary satellites that just fan everything. So we're almost to a point where we can find a certain signal strength that we can just almost accept from SpaceX, because there's always going to be something, right? We're a receiver with 85 dB at 12 gigahertz, so we're always going to see something. But it's been really, if they had never coordinated with us, we would be blown out of the water and probably never be able to look in those bands. But because they are coordinating and their systems are so dynamic, it's really cool to see where we've come. And I think there's a good place where we can all kind of meet in the middle. And if after this, if you want to email me back and forth about more Starlink questions, I'm happy to answer them. Or Chris Dupree is leading a lot of those coordination efforts, so we go back and forth all the time about how this impacts us. A lot of the work Starlink has put in, talking with their engineers, and yeah, it's actually a really cool project.
Okay, cool. Let's see. Anyone else have any other questions? Okay, I have one. I can't resist.
Mhm.
All
Yeah,
right. You were talking about, was it the Teslas that did not want to install the AM radios because of interference?
right. Yep.
Oh,
Yep. So a lot of electric cars are starting to experience this problem where I don't know exactly what it is in their systems, but the AM bands cause significant interference that has led a lot of these manufacturers to either not put AM radios in the car and try to push AM out of the water, or it would take a very large redesign of a lot of their infrastructure that they just are not going to do. Uh-huh.
interesting.
Do you
Yep.
think
That's
it's specific components in like their circuits?
I can't remember off the top of my head, but I think if you give that a quick Google search, you should be able to find it pretty quickly because it's very public out there about why it is. But yeah, it's some sort of component that would just cause some sort of interference to the actual car and would not be good for them.
that's interesting. Because I think I did see an article a while back about the elimination of AM/FM radios altogether
Mhm.
because people could stream using the internet connections that some of the radios had. I did not hear about the interference. I'm going to Google that.
Yeah, yeah,
That's
give
really
it a Google.
interesting.
Yeah, because then there's
That,
also, AM is used a lot in emergency situations currently. So that would take a whole infrastructure redesign. So it's like, who's going to step in eventually and make one of them choose? It's going to have to happen eventually.
yeah, it's funny because I would imagine, it's just so funny. I would imagine, well, I'm old enough to remember some of the old cars and the old alternators, and they would cause all kinds of interference on the other direction. In other words, you could hear them on your ham radio, especially using amplitude modulation. You could hear they would be really loud. And it's kind of funny. It's a holdover, but I have some of the newer transceivers. Like I'm looking at one right now, has a noise blanking system in there where they essentially throw a capacitor and some other filtering circuits across the power lines to cut noise coming from the engine. Uh, but I'm going to look that up. That's really interesting. Um, and that's really fascinating.
Yeah.
Uh,
There's
I,
there's a lot of really strange car frequency things that kind of pop up the more you look around. Like for example, at Green Bank, all of the downsite vehicles are diesels because spark plugs cause pretty significant interference. Or one of the new things that we're trying to, or some people on site have figured out is, I want to say it's right around 300 megahertz. Your tire pressure sensors
oh
that are
yes.
communicating. Yep. Yep. So someone saw some blips in a data in some sort of data point and did some digging and found out it's probably from a tire pressure sensor from a car. So it's like things like that that you would never even think of.
That's really interesting because 300 megahertz is also the frequency a lot of key fobs operate at,
Okay.
and also garage door openers. I think they're also around 400 megahertz or so. And I'm chuckling because in this area we had a problem with a radar system, believe it or not, in Virginia, northern Virginia. I think it was based at the Quantico Air Force Base. And the story goes that they would fire up this radar and people's garage doors would open up
That's funny.
and open and close and then start to close and then stop and all kinds of stuff. And so eventually they resolved it. I think speaking of spectrum management, I think what they did, there were some modifications to the radar system and also uh, the key fobs that were used to control um, the garage doors and also to open and close cars changed too. They switched to a spread spectrum like mode of operation. Instead of camping on one frequency, they would hop.
Okay.
around, and so that sort of mitigated the problem. But it's kind of a funny thing. That's part of what hams have to deal with, is being good neighbors
Yeah.
with all the
Yeah.
people. I've got the same NTA chart up here in my office behind my head to remind me that we're a service that shares frequencies with others, and we need to be thoughtful and mindful of that, you know. So it's just, I'm going to look that up about the AM radio. That's really interesting. Um, well, let's see. How are we going here with time? We've got like 7 minutes left. Um, I don't have any other questions. This is really a great talk. This is really very interesting. When I got my ham license, ham was, or at least we thought, was verboten in the National Quiet Zone. So it's kind of cool to see all this kind of coordination. I think that's really good. And the other thing I'm going to check, class, is to make sure. I think there are references to the National Quiet Zone in the Red Book and the license manual. I'm going to make sure that they don't say that you can't use any radio at all. I'm going to make sure it's accurate and check on that. I'm sure other people have done that. It may be that it doesn't show up into the general class license. This one is for the technician's license. So I'm going to check on that. There's a couple pieces of homework I'm going to take away from this talk. This was a
Okay,
great,
cool. Yeah.
great
Let me know
talk.
if you have any questions. The best place to look is probably the Summits on the Air website. I think I put the link in the PowerPoint mainly for that reason. It's probably the best resource for explaining, what the coordination is like, why it is the way it is, just because we've reached out with them and communicated with them so many times because they wanted to get it right because they have so many members a part of SOTA. So that's probably the best resource.
Okay, yeah, I'll follow up with that because I'm interested in POTA.
Okay,
I
yeah,
haven't done any activations, but I think there's some national parks not too far from the national coordination zone.
yeah,
So it'd be interesting to know, and I'm sure the POTA people are some of the same people as the SOTA people. So it'd be good to I'll follow up on that as a personal
sure,
thing
yeah, yeah.
because I'm curious.
I've definitely interacted with some POTA people before. I couldn't remember who, I couldn't remember where to dig it out to get the accurate information. I knew the SOTA people better, so that's why it ended up in the presentation.
Well, this is one of these things about ham radio. There's so many different aspects and sub hobbies, and POTA people are probably SOTA people, you
Yeah,
know,
exactly, exactly.
you know. So I'm definitely going to follow up. I just want to make sure, class, are any other questions? Well, okay, nothing heard. Well, Shelton, thank you so much. I really appreciate this. Is great. You're probably going to get bombarded by
Yeah,
lots of
no,
emails.
please feel free to reach out. My email is on the title slide. I'll just send you my PowerPoint as well.
Oh, that'll
And
work.
yeah,
Yeah,
okay. I know you're
that'll.
recording as well, but yeah,
Yep.
my LinkedIn is also up there. Feel free to
Oh,
reach out and connect with me on LinkedIn. Happy to answer anyone's questions. This is a great class. I'm happy you guys are all in it, and yeah, feel free to reach out.
all right, definitely. And I also want to thank, before I say seven things, I want to thank Aaliyah for coordinating and setting this one up. This is great. We're looking forward to some more great talks. Um, unless anyone else has anything to add or say, I just will wish everyone 7-3s best wishes. Have a great night. And the recording will be available tomorrow.